Well, I think it's possibly about the right time to make a start. We have about 100 people on board so far. There are still people joining, but we'll anyway make a start. So good morning to those of you in Europe and Africa. Good afternoon and evening to those of you joining us from Asia, and a very warm welcome to you all. Thank you for joining this, the fourth of our regular series of short courses on pumping topics. This one will last about 35 to 40 minutes, allowing us the time for a Q&A session after the presentation. Those of you who attended any of the earlier sessions will know that we're deliberately steering away from product presentations and towards educational content, addressing a different pumping topic in each one. But having said that, please forgive me 4 or 5 brief slides to remind you who we are and what we do. Okay. We are Ruhrpumpen. We are truly a global company these days, one of the big boys, with 70 years of experience, over 70,000 pumping solutions installed worldwide, and manufacturing facilities in 10 countries now. 10 countries, 5 continents, 1, 2, 3, 4, 5. We're in all the markets that you're in: power, water, chemical, industrial, and probably most important to us all, oil and gas. A very wide product range, as you'd expect. Single stage overhung pumps, foot mounted or centerline, ANSI, ISO, general purpose or API 610. Between bearings pumps, axially split, radially split, API 610 again. Horizontal multi-stage pumps, again, axially split, radially split double case. A wide range of vertical pumps, multi-stage pumps, and big axial flow pumps. We also manufacture vertical multi-stage pumps, double case and single case, VS6 type and VS1 type, and also submersible type. Positive displacement pumps, magnetic drive pumps, and package systems. I have added a few slides right at the end of the presentation as an appendix, showing the full range of our products. But I don't plan to spend any time on that right now. You can take a look at your leisure when you get a copy of this session. So that's the end of the commercial, and this is what we're going to be talking about today. We're going to be looking at selecting the right pump for the application. It's aimed at process and mechanical engineers and consultant engineers specifying pumping equipment, as well as applications and sales engineers selecting and quoting them. The aim is that you develop an understanding as to which type of pump is appropriate for different applications. So we'll cover such topics as when to transition from an OH2 to a BB2, when to consider VS6 pumps, and barrel pumps versus horizontal multi-stage pumps. We will be covering the main range of pumps used in the oil and gas industries. I'm not going to try to cover chemicals, water, general industrial, or fire. There's a limit to the useful information I can impart in 40 minutes. You will find that there's an awful lot of detailed slides here, primarily range curves. Now, I don't expect you to take them all in. I'd suggest you print the curves off, laminate them, and put them in your top drawer for easy access. We will be holding a Q&A session at the end. Now, unfortunately, the nature of a Zoom format for these seminars makes a fully interactive Q&A impossible, especially with so many attendees. Let's see, how many have we got at the moment? We have about 150 attendees at the moment, and we had over 200 attendees for each of the previous sessions. So it won't be fully interactive, but we'll do the best we can. Please use the Q&A facility at the bottom of your screen to ask any questions or make any comments. I'll address those that I can live at the end of the session, and the rest will address by mail in the coming days. We are recording this session and we'll make it available to all attendees as a YouTube link, as well as by emailing you a PDF version of the slideshow. So let me get back to the slideshow. Here we go. Okay, so we're going to look at a couple of scenarios. Scenario A, you are a process engineer or a mechanical rotating equipment engineer, and you have preliminary process data for a pump duty. 200 cubic meters per hour, 200 meters head, 5 meters MPSH available, specific gravity of 0.7, temperature 150 C, and we're in a 50 cycle facility. So what sort of pump is this going to be? Well, at this early feed stage, you probably don't want to waste the pump vendor's time by asking, so you go with your gut and you say OH2. Are you right? Well, I'm going to give you the tools to be able to check this out and to save you from possibly getting yourself into trouble by making a bad guess. Scenario B, well, it's the same situation, but from a different viewpoint. This time you're the salesman or applications engineer, and your customer, the aforesaid process engineer in scenario A, has asked you to have a look and say, what sort of pump do I need for this duty? Just a quick check, don't spend long on it. So what do? You probably plug it into your pump selection program and see what it spits out. Well, I did that. The program defaults to listing possible selections by efficiency. The first 3 compliant selections are BB3 axially split case multistage pumps. Next, we have a couple of BB2s operating, I don't know if you can see, well back on the curve. Then we get a BB2 two-stage pump. A couple of non-compliant pumps here, and then finally, in 7th and 8th positions, we get an OH2. So what did you do? As the applications engineer, the sales engineer on this, did you go back to your client and say, it's a 3-stage BB3, nice selection, bang on BEP, and 76% efficient? Well, I hope not, because it's blatantly not a BB3 duty. So what do we learn from this? What we learn is that, firstly, pump selections are stupid. That they are a great tool, but a poor master. And finally, and most importantly, always know the pump you expect to see before you use the pump selection program. Again, I'm going to give you the tools to be able to check it out in advance and save you the possibility of making these mistakes. So here is what you do. You start with the least expensive option, an OH2 pump. I mean, the duty I gave you, 200 cubic meters an hour, 200 meters, it feels like an OH2, doesn't it? This will be a good place to start on any search. So here we have the OH2, single stage, single suction, the refinery workhorse. It's not great on NPSH, and it's not great on high suction pressure duties, say 20 bar, 30 bar suction pressure. Here are 4 range curves. 2-pole, 50 hertz. 4-pole, 50 hertz. 2-pole, 60 hertz. And 4-pole, 60 hertz. Print them off, laminate them, and put them in your top drawer for easy access. Now we go back to the 50 hertz 2-pole. Here we go. And we look at the duty, 200 cubic meters per hour at 200 meters head. And we see that it's comfortably within the OH2 range. You can't read the actual pump sizes in this chart. Well, you can if you zoom in far enough, but that's not the point of this exercise. We're talking broad brushstrokes here, the big picture. What we see is that here in the middle of the pack is an OH2 that can probably do your duty. Now, never mind that this is these are Ruhrpumpen range charts. This is a fiercely competitive marketplace, and you'll find that most manufacturers have very similar ranges. So if Ruhrpumpen can do it, then so can most of the others. But don't just take my word for it. Here's the Flowserve published range chart superimposed on the Ruhrpumpen one. As you see, almost identical. Looks like they've got an outlying pump here. Flowserve has that pump that Ruhrpumpen doesn't. But by and large, if you are in with the pack here, then you know that Flowserve and Ruhrpumpen can do one. Same again for Sulzer. And the same again for Gould's. I have similar slides for Gabionetta, Apollo, Enseval, and Finder, and some others, I think, as well. Now, you won't be getting these last 3 slides in the final release presentation, but you've seen them anyway. So, having established that the flow and head falls on an OH2, and remembering that OH2 pumps aren't great on NPSH, we now ask the question, do we have enough NPSH available? Well, I've made a simple NPSH suction specific speed calculator for you to be able to check this. It's an Excel sheet. All participants will get a working copy of this calculator when we send out this session's slides. What this calculator does is to calculate the suction specific speed of the theoretical pump that meets your NPSH available with the normally accepted industry standard of 1 meter margin. Let me back off a minute here. You don't all know what suction specific speed is. Here is the formula for calculating suction specific speed. And you can consider it to be a dimensionless number. And it describes the NPSH performance of a pump. The higher the suction specific speed, the better the NPSH performance. So in this example, we had 200 cubic meters per hour at 50 hertz speed, so 2960, with 5 meters of NPSH available. The program has calculated the suction specific speed and tells us that it's a single state suction pump. If it's a single suction pump, then it would have a suction specific speed of 12,759. Now, the industry has, for various reasons, mostly erroneous, set a maximum value of suction specific speed of 11,000 in US units or 12,760 in metric units. I'm not going to go into this in detail today. I'm going to do so in session 5 on NPSH and suction specific speed in 2 weeks' time. Nearly all pump vendors have given up trying to fight this limitation, and we've designed most of our hydraulics to be within this 11,000 limit. Excuse me a second. So in this calculator, if the suction specific speed shows up as being above 11,000, then you get this warning to reduce speed or increase NPSH available. Or you can select a double suction pump, which will be within the 11,000 limit. But of course, a double suction pump, a BB2, is considerably more expensive. So let's go back and look at our options. First one, we looked at 2-pole and we saw that it was a good selection, but the NPSH was too high. So, and the program suggested look for a slower speed. So is there a 4-pole OH2 selection available? We look at the 4-pole chart, 200 cubic meters an hour, 200 meters head, clearly not. Next, can you find a bit more net positive suction head available? Going back to the calculator, this time I've plugged in 6 meters instead of 5 meters. And we see that we have a pump, 10,792 would be the theoretical pump that would do that duty with a meter margin. And that's less than 11,000. So you can be certain it's success. There is probably a suitable single suction pump for your NPSH condition. And that'll be from several suppliers. You're good to go if you can find yourself an extra meter of NPSH, maybe by lowering the pump or raising the suction pressure. Next option would be, if you couldn't find more NPSH, then you have to say, well, okay, let's have a look. Is there a BB2 pump available? Here's a BB2 pump, top suction, top discharge. It's a double suction pump, so it has a lower net positive suction head requirement. Why? Well, the flow comes in here, splits into two, half goes into one side of the impeller, half goes into the other side of the impeller. You have twice the eye area compared with a single suction impeller. The flow's going into both sides, so twice the area, half the pressure drop on inlet into the impeller. And that's what NPSHR is, the pressure drop as the flow goes into the impeller. So you'd expect a BB2 to give you a lower NPSH solution. Let's have a look. 200 cubic meters an hour, 200 meters head. Well, it's possible, but it's not a good selection. It's about 60% of the BEP flow for this pump. So that's a non-starter. You just don't select a pump back there. So a BB2 pump is not an option for you. Your only remaining options are is an inducer acceptable? You can check that with your client. Or is a higher suction specific speed impeller acceptable? Most pump manufacturers still have impellers that have a higher suction specific speed than the 11,000. They'll have ones that are around 12,000, 13,000. With good users lists, it's a possibility, but what will your client allow? And the non-answer is to select the 3-stage BB3. Do that, you've probably lost the project. Okay, we'll leave this example duty behind now. It's served its purpose. It's shown us that the logical way to progress through any pump selection process is to look at the OH2 first, then the BB2. So here are the BB2 range charts. 50 Hertz 2-pole, 50 Hertz 4-pole, 60 Hertz 2-pole, and 60 Hertz 4-pole. Again, as with all the curves I show today, most vendors will have very similar ranges. We may have an outline pump at the extremes that others don't have, or vice versa, but within the bulk of the chart, we'll have similar range coverage. Moving on, still in the BB2 type, this time 2-stage pumps, suction, discharge, top configuration. There's a sectional drawing, here's the suction. So the flow comes in here, down this channel, into the first stage, gets thrown out by the impeller into this crossover, into the second stage. It's thrown out by the impeller, and the discharge is here, here, obviously not shown here. There's the range charts, 50 Hertz, 2-pole. Looks like it gets you to 800 cubic meters per hour and 600 meters of head at 50 Hertz. Or if you're looking at 60 Hertz, we're talking 4,000 gallons a minute and 3,000 feet of head. Notice that there is a double suction available on some of the larger sizes to reduce the NPSHR. So you've looked at an OH2, you've looked at a BB2, you've still got an NPSH problem. We haven't been able to offer you a pump that meets your NPSH. So next one to logically look at is the VS6 pump, which is traditionally used when you have very low, even 0 NPSH at grade. It works on the basis that if you have 0 NPSH at grade, then 3 meters down, for example, you have 3 meters of NPSH available. So we make the pump long enough by adding spool pieces in here to position the first stage impeller low enough to give you your impeller, to give you your NPSH margin. But it's not just an NPSH saver, it's a space saver as well. 20% of the floor space of the equivalent BB2. It'll also save you money. It's a cost saver. One seal, one sealing system, it's less expensive than the equivalent BB2. But there's a downside. Civil engineers don't like digging holes. Well, there can be good reasons for this, such as water tables and groundwater quality. But if you can persuade them to do so, you're saving all the way. Big uses for these pumps: light hydrocarbons, C2, C3, C4, condensate water in power stations, ammonia, liquid oxygen, liquid nitrogen. Here's the range chart for the semi-engineered or modularized range of these pumps. So to about 1,000 cubic meters an hour and 850 meters of head. If we're looking at 50 hertz, or if we're looking at 60 hertz, 5,000 gallons a minute and 4,000 feet head. We also have an engineered range. This has got some very large flow pumps, as you can see up here to 25,000 gallons a minute or 5,000 cubic meters per hour. Commonly used on hydrocarbons and in water service. Now on to axially split case pumps, type BB1 and BB3. These are most commonly seen as pipeline pumps for both oil and water pipelines. Now, API 610 puts a limit on the use of axially split pumps. It says anything over 200 degrees centigrade, or if the SG is less than 0.7, or if the discharge pressure is greater than 100 bar, then you need to offer radially split. You can't have an axially split case pump. The reason for this, they're largely concerned about leakage through and past the flat gasket that seals the upper case to the lower case. These limits, they're very conservative, and API does accept that some manufacturers have excellent installation lists of pumps that exceed these limits. I'll mention that more in a minute and illustrate it on a BB3 pump in a minute. It's a very interesting subject. I'm not going to go into it in great detail here now at all, in fact. But if you're interested and you want to know more on this subject, have a look at this reference by the pump guru, Simon Bradshaw. So first, the single stage version. Is the two poles 50 hertz, and 60 hertz, both on the same slide. 4-pole, 50 and 60. 6-pole, 50 and 60. And 8-pole, 50 and 60. You see we have some very large pumps that go out here to 50,000 gallons a minute, 10,000 cubic meters per hour. Moving on, multistage, type BB3. This has back-to-back impellers, meaning half of them facing one way and half of them are facing the other way. Let me show you how the flow goes. There's a suction nozzle you can't see here, like that one, but on this side of the pump. So the flow comes in here to the first stage impeller, spits it out into the second, into the third, into the fourth, into the fifth in this 10-stage pump. And the discharge from this fifth stage comes into this crossover, into the sixth stage, seventh, eighth, ninth, 10th, and then out here. The back-to-back impellers balance the thrust. So you have just one lightly loaded thrust bearing here. Here is the joint, the flat joint, that API 610 is worried about leakage from. Note how our design has interstage bolting to ensure gasket compression in this area, which will prevent washover between stages, particularly at the center bushing where the delta P is greatest. Here's an example of washover erosion on a pump which doesn't have interstage bolting. Now, we're not unique in having this design. Flowserve does it similarly, I know that, and I can well recall from my days with Flowserve pointing out to customers how many pumps we had in propane or butane service of this type. Here's the range chart for the smaller, lower head sizes. So 300 cubic meters an hour, 700 meters head, or 2,000 gallons a minute. Let's see, 2,000 gallons a minute, and 3,000 feet head if you're talking about 60 hertz. The larger sizes, 1,250 cubic meters an hour and 1,500 meters of head for the 50 hertz, and at 60 hertz, 6,000 gallons a minute and 6,000 feet head. Now finally for today, double case pumps, type BB5. Used when you have no other choice. High pressure, low specific gravity, and not allowed to use a BB3. It comprises an inner case and an outer case, the outer case being the pressure boundary. The inner case might be axially split, as in a BB3, or more commonly, it's a radially split diffuser design. Impellers are sometimes in line, or as in this case, back to back. So let me show you the flow path again here. Suction comes in here, into the first impeller, through to the second, through to the third. It then crosses over through this passage, into the fourth, fifth, sixth, and finally comes out here. It's usually built as a cartridge pull-out design. So what you do, you pull out the inner case and carry it off to the workshop for disassembly. I am planning to do a more detailed session on BB5s later on in the year. So here's your range chart. 11,000 cubic meters per hour, 1,100 cubic meters per hour, I do beg your pardon. 1,100 cubic meters an hour and about 2,778 meters of head, or in 60 hertz, 6,000 gallons a minute and 13,000 feet head. That's where I'm going to leave this session for today. We've covered the main range of pumps used in the oil and gas. And I've not tried to cover chemicals, water, general industrial, or fire. As I said, there's a limit to the useful information I can impart in a 40-minute session. I apologize that there were an awful lot of detailed slides here. And as I said in the beginning, I don't expect you to take them all in. I'm not going to hold a pop quiz or anything like that. I'd suggest that you print the curves off, laminate them, and put them in your top drawer for easy access for next time you're speccing or selecting a pump. So it takes us to the next thing, which is the coming attractions. NPSH made simple, or simpler anyway. This is one of the most difficult and misunderstood concepts in pumping, and I intend to give you a simplified version of it. I'm not going to make you pump experts, but I'm going to give you the information to fully understand how NPSH affects you guys. Thursday, the 1st of July, again, 2 sessions, one at this time for the Eastern Hemisphere, so that's you guys, and one later in the day for the Western Hemisphere. The invitation will be published very soon, so put it in your diary, 1st of July, 2 weeks today. Then we're going to take a break from these short courses during the holiday period of July and August. We'll resume in September. I've already got several topics in mind, and I'll be adding to them in the coming months, in the coming weeks. I'm going to leave this meeting open now for a little while to allow you to post in the Q&A box. I can see we've got a few comments there already. And I'm going to endeavor to answer those that only need a short answer here in the next 20 minutes or so. Those that need a fuller answer, I'll get you a written answer in the next few days. If you think of anything later on that you want to ask, info@ruhrpumpen.com is where to send it. Our marketing team are standing by to direct your questions to the best person to answer them, and they will be sending you the YouTube recording and the PDF of this presentation and the NPSH suction specific speed calculator. If you need a certificate of completion for this short course, again, info@ruhrpumpen.com. Now, on with the Q&A. Let's see what we've got. Okay, we have one. Adnan Safraz says, how does an inducer help to work pump with low NPSH? That's not something that I can give you a quick answer on. An NPSH, an inducer acts to help the flow into the impeller. It's a very high suction specific speed, 75,000 suction specific speed device, and it just has a very low NPSH. There are limitations to it as well. It restricts the operating range. You get a reduced operating range for the pump. So there are pros and cons. They're increasingly acceptable these days. I'll try and get you a better answer in writing. An anonymous attendee here has said, another thumb rule for selection between OH2 and BB type is product of power and speed if it's above 450,000. Is this understanding correct? Yes, it is. That really determines when you have to move to a high energy pump, a BB3 and a BB5. If it will fall on the range of an OH2 and a BB or a BB2, that is the right pump for the application. You haven't got to worry much about this power and speed product of 450,000. Another anonymous attendee here. For any OH2 proven model, can pump suppliers customize performance curve shape, i.e. increase or decrease head rise to shutoff and BEP flow, or they cannot customize? We can make slight changes to the shape of the curve. There are techniques of underfiling and overfiling, for example, of V-notch grooving of the impeller, which can make small differences to the curve shape, but we can't substantially change it. When we tend to use those techniques are if a pump on performance test doesn't perform quite like its expected curve. and then we can do some rescues to bring it back into shape. It doesn't make a big difference. Gino Catalan says, does RP have OH3 models? Are they the same geometry as the OH2 models? Meaning, are they interchangeable? Yes, we do have OH3 models. Some of the impellers would be the same ones that we use in the OH2, but by and large, it's a completely different pump range. The geometry of them is similar to the OH2. They're a single suction volute design, certainly not interchangeable. We have here a question from Panagiotis Fletsas. Apologies if I didn't pronounce that very well. Hello, sir, and thank you. Is there going to be any session on mechanical seal selection? And that is one I've got in mind. I think to do that one, I'll probably have to get into partnership with a mechanical seal supplier because they're the experts in this. So yes, I do have it in mind, maybe a joint session with a mechanical seal supplier. Omar Dehmani says, as sales, what can we do if the client didn't provide the NPSH? Well, all you can do is tell them what the NPSH is that you require, and it's up to them to provide it. Really, you should ask, what is the NPSH available? If you don't ask, you're bound to end up in trouble. Akram Edgain, why may the client refuse to go for an inducer? There is still a lot of feeling against inducers. One of the problems that they do experience is a limited operating range. Normally, they operate sort of plus or minus 20% from their design point. Well, if you want a process pump, you're probably going to operate it from run out to shut off. And an inducer frequently has a higher NPSH away from its design point than it would do if it wasn't there at all. So again, it's not a cure-all. If you know where you're going to be operating, you can consider an inducer. It's a good option. And inducer design over the last 30 or 40 years has come on hugely. And there are some very good inducer designs out there now. Jan Kowalski has said, concerning multi-stage split pumps, which design, axially or radially split, is more inspection friendly, especially in confined chemical plants? Excellent question, thank you. The axially split case pump is far more inspection friendly. Once you've removed the bolts and lifted off the top case, you can inspect it and see whether you have a problem, whether you've got wearing clearance problems, if there's wear or anything. You still have to take the rotor back to the workshop to dismantle it, but in the field, you can actually see if you have a problem and possibly not have to take it out altogether. Whereas with the double case diffuser design, with the double case design at all, you have to take out the inner cartridge and take it back to the workshop to have a look at. So you've got no idea until you get it back to the workshop what has happened with it. Dele Aludare says, are you sending the NPSH calculator to our email? I'd like to go through before asking questions. Well, yes, certainly you'll be getting that along with the presentation. And sure, if you have questions after that, come back to us. Kedar Dami says, OH2 and BB type. As an end user, Which one option is better? Neither is better than the other. It depends on the flow and head. There's little to beat an OH2 pump for lower flows and lower heads. BB2 is better for higher flows. Jivan Mali says, how does suction specific speed affect the operating range of the pump? Yes, that's a very good question. Very high suction specific speed pumps have a more limited operating range. It's something that I will discuss in the next session in 2 weeks' time on NPSH and suction specific speed. But yeah, if you've got a high suction specific speed, say in the region of 13,000, 14,000 US units, you don't want to be operating that back to the left on the curve. Anonymous attendee has said, should we still limit selections to 11,000 suction specific speed? What are the instances we should justify deviation from this requirement? Excellent question. Firstly, it rather depends what your customer's specification says, what the end user specification. It might have a fixed requirement that you not exceed 11,000. If it does, the chances are that you won't be allowed to deviate from it and you'll have to select below 11,000. And that's why most pump companies modified our ranges so that we've got pumps at 11,000. Nevertheless, we still have a lot of pumps that are at 12,000 or 13,000 suction specific speed. And these have better NPSH performance. You would have to justify it with your client on a case-by-case basis. Talking about particularly the range of operation, the vendor's experience with that pump, and address particularly concerns over operating back towards shutoff on that one. It is something that I will go into in more detail in 2 weeks' time on the session on NPSH and suction specific speed. Can a manufacturer use a large impeller eye and nozzle to lower NPSH R, which is a high suction specific speed impeller? Yes, that would be exactly the case. I mean, a higher suction specific speed impeller has probably got a bigger impeller eye diameter. So again, if you're allowed to use a pump with a higher suction specific speed, go for it. It'll have a lower NPSH. Another one, anonymous attendee, is NPSH critical in providing a pumping solution? In what conditions can we calculate it by ourselves? You can't calculate NPSH, it's measured. A pump during its design will have been performance tested and NPSH tested on that, and so we'll know. I mean, they would have predicted what the performance on NPSH will be, but this is for hydraulic engineers to work out who fully understand the design they're putting together. In the field, the users, you can't calculate the NPSH. You can only read it from the curve that you've been provided by the pump company. Anonymous attendee, is your NPSH calculator based on Ruhrpumpen design, or is it valid for all the other pump manufacturers? Oh yeah, it's valid for anybody. It purely, all it does is calculates the suction specific speed given the NPSH and the speed and the flow rate. It takes those three and it calculates suction specific speed. So it doesn't matter if it's a Ruhrpumpen pump or a Flowserve or a Sulzer or anybody else's pump, it will work for anyone. Within the OH2 pump casing, can pump suppliers offer different impeller design or geometry, or one design combination of casing impeller is fixed? Varies a little bit from supplier to supplier. Frequently, there might be two impellers which might well fit a casing size. You might call it the low flow impeller and the high flow impeller. So the casing will probably have been designed to take more than one impeller. Is the pump failure rate higher for higher suction-specific speed? Not if it's a well-designed pump operating properly. I'd like to defer that question until 2 weeks' time, and we'll address that there. That is exactly the argument that was used for not selecting high suction-specific speed. But there was one problem they made with that one, which was it's just not true. Or it's very limited truth. It's a bit like the measles, mumps, and rubella vaccine causing autism. What happened is that autism starts to appear at about the same stage, same time period that you get a vaccine against measles, mumps, and rubella. So you can say, oh, the two must be linked. Well, they're not. They're just contemporaneous. They happen at about the same time, but there's no causal link. And that was the same thing with high suction specific speed. The guy who first produced the paper on this said, look at all these problem pumps, and they have something in common. They're high suction specific speed. Well, yeah, that might be the case, but that wasn't the reason for it. The reason for it was usually that they were very difficult pumping applications. They were pumps operating with very low NPSH. They were operating back on their curve and various other nasty scenarios. So it really wasn't the truth. A well-designed impeller operating in a pump that is operating at its design point or within the range that the pump vendor has proof of good operation, that'll work fine. Modern designs are much better than the old 1950s design that were giving the problems that resulted in this paper. A three-stage pump with a vertical clearance on the shaft or impeller. How do I resolve the problem? This is from Dele Aludare. This is a specific question, and I think you really need to go back to the pump supplier on that and address it. I can't give a general answer on that one. Alex Wainwright, low head and high flow. Is there an accepted pump type? We know VS6 is good for the opposite scenario. Low head, high flow implies an axial flow pump. Depends how low, how low the head and how high the flow. For example, I did show that the VS6 pump, the engineered type VS6 pump with axial flow impellers would certainly give you low head and very high flow. And so it's commonly used in waterworks and water treatment plants. Panagiotis Vletsas again, does the Ruhrpumpen online pump selection tool require all fluid properties that may not be available at the time for a quick pump selection, or it works with limited information? Thank you. Yes, it will work with just flow and head and speed. That's the minimum information. The more information you start putting in, the more it will refine refine its selection. So if you know the NPSH, it'll take that into account. If you know the specific gravity, if you know the NPSH available, if you know the temperatures, it will take these into account and refine the selection. But yes, it will work just with flow and head. Okay, that appears to be all the questions I've got here at the moment. If I've missed any, I will be checking up on it anyway and giving written answers to all these anyway. Let me look now at the chat in case there's something in here that should have been in the Q&A. Yes, here's one. For cryo service, what would be the casing and rotor material of construction? Again, it depends. If as the temperature goes down, you start needing to use low temperature steels for a start. And when you get to a certain point, you switch over to stainless steels. We do have good service on some VS6 pumps in liquid oxygen, liquid nitrogen service, where we are using aluminium, bronze, and cupronickel. Someone here, Simone Gabrielli, has said, where will the slides of this session be available? Well, if you've registered with this, for this session, then we have your email address and you will automatically be getting the slides of this session in a few days' time. What is the email address for questions that you gave previously? Can I send a request for quotation to this email address? That's Tamar Zubari. Yeah, it's info@ruhrpumpen.com. info@ruhrpumpen.com, and we will pick that up and get it to the right sales office to be able to give you a quotation. Okay, I think that's covered everything that I can answer here. There may be a few more that I can answer in a written format. So thank you very much for attending today. I thoroughly enjoyed preparing for it and presenting it. I hope you found it useful, and I look forward to seeing you in 2 weeks' time. Yes, on the 1st of July, when we'll be talking further about NPSH and suction specific speed. Thank you and bye-bye.